In this video, we're going to look at strategies specific for balancing combustion reactions, which for many students are the most frustrating type of reactions to balance. So in addition to the major hydroxide and grouping polyatomic ion strategy, the primary strategy when dealing with combustion reactions is to determine whether we have an even or an odd number of each of our reactants or products within the combustion reaction. The easiest way to visualize this is to actually try it, which we're going to do with these first two combustion reactions. So before we do that, though, let's start off by applying the major hydroxide strategy, and we can see that in a combustion reaction, the only element that is not oxygen or hydrogen is carbon. So we see that we have 6 carbons in the reactants, so we can add a balancing coefficient of 6 here, and now our carbons are balanced. Now, if we do the same thing with hydrogen, we're going to do hydrogen first because we have 2 molecules that each contain oxygen, but only one that has hydrogen. So let's deal with hydrogen first. So if we have 6 hydrogens in the reactants, we have 2 in the products here, which means we can add a balancing coefficient of 3, because 3 times 2 is 6. However, according to our even-odd strategy, this would give us a problem here. Because water has an odd number of oxygens, because it has 1 oxygen, so multiplying 1 by an odd number will give us an odd number. We can see that as long as this balancing coefficient is odd, we will never be able to balance the number of oxygens, because O2 is an even number, which means that in order to balance oxygen, we need an even number of oxygens on both sides of our chemical reaction. Now, there is a simple way that we can modify our balancing coefficients without really changing anything in order to make sure that we have an even number of oxygens in water, and that's simply to take the whole equation and multiply everything by 2. So if we only have 1 of our organic hydrocarbon, let's put a 2 here so that we have 2 C6H6 molecules. We know that 2 times 6 is 12, so if we take 6 and multiply it by 2, we would get 12 carbon dioxide, so carbon is still balanced, and then if we take 2 and multiply it by 3, we would get 6 water molecules, and because we now have 6 oxygen in water, our number of oxygens is now an even number, and all we need to do is figure out the balancing coefficient for oxygen now. So finally, we have 12 times 2 is a total of 24 oxygens in carbon dioxide, and 24 plus 6 is a total of 30 oxygens in total for the reaction, and 30 divided by 2 is 15, which means that oxygen is now balanced. So this is how we apply the even or odd strategy, by seeing whether we need an even number or odd number of each of the oxygens or hydrogens in the chemical reaction. If we take a look at the second example here, if we rewrite our organic chemicals formula so that it's easier to read, there are 6 carbons, 5 plus 1 is 6 hydrogens, and 1 oxygen here. So that tells us that we have an odd number of oxygens from this compound here, and we already know that because water has 1 oxygen, we have an odd number here, which means we don't need to worry about converting every compound into an even number here. So let's go ahead and apply the major hydroxide strategy by balancing the only major element, the only non-hydrogen and oxygen element, which is carbon. We have 6 carbons in this organic hydrocarbon here, so let's give a 6 in front of carbon dioxide. Now we have 6 hydrogens here, so 3 times 2 is 6, and because we have an odd number of oxygens on both sides, we don't need to do anything more here. So let's simply count the total number of oxygens in our products to find out how many oxygen gas molecules we need. So 6 times 2 is 12 oxygens in carbon dioxide plus 3 oxygens in water, means that we have a total of 15 oxygens in total. Now we have 1 oxygen over here, which means that we would need 14 oxygens from oxygen gas in order to balance this completely. So 14 divided by 2 is 7, and that allows us to balance oxygen completely. And again, we can see because we have an odd number of oxygens on both sides, this balancing works. Now, our final strategy specifically involves incomplete combustion reactions, which tend to make students go a little bit crazy because we can see that because incomplete combustion reactions produce carbon dioxide, carbon monoxide, and elemental carbon, we have more than one location for carbon and more than one location for oxygen. In fact, we've got 3 locations for each atom. Now, this tends to cause a lot of frustration because students are under the impression that there is only one way to balance each of these reactions, but this is not actually true for incomplete combustion reactions. We can see that we can actually balance this reaction in multiple ways. So if we start with our major hydroxide strategy, we have 6 carbon atoms in the reactants. So let's make 6 carbon atoms in the products here. So let's go ahead and, for the sake of argument, give ourselves 2 of each of our carbon compounds here. Then if we try to balance out hydrogen, we have 14 hydrogens in the reactants, meaning that we would need to do 14 divided by 2 is 7 hydrogens, or 7 water molecules rather, to balance out the hydrogens. But now we see that we have an even odd problem here. We know that our reactants must contain an even number of oxygens because O2 cannot ever be an odd number of oxygens here, but we see that we have odd numbers in our reactants here, or our products rather. So let's modify our CO2 or carbon monoxide balancing. Let's say that instead of 2 carbon dioxide and 2 carbon monoxide, let's say that we have 3 and 1. So that way, if we count the number of oxygen, we have 3 times 2 is 6 oxygen in the carbon dioxide molecule, plus 7 oxygen from water, plus 1 oxygen from carbon monoxide. 6 plus 7 plus 1 is 14 oxygen, which is an even number. 14 divided by 2 is 7, and we can see, even though we changed how we balanced carbon, we still have 6 carbon in our reactants, and then 3 plus 1 is 4 plus 2 is 6 carbon in our products as well. So if we add a balancing coefficient of 1 here, we see that this is one way that we could balance our reaction. Now let's look for a different way that we can do this. Let's go back to the original problem that we had, where if we put a 7 here to balance out water, let's change the way that we rebalance our carbons. So let's say that if we would have 2 carbon dioxide here, now let's say that we have 3 carbon monoxide, that would give us an even number of carbons, because 2 times 2 is 4 oxygen. Then we have 7 oxygen here and 3 oxygen here. 4 plus 7 is 11, plus 3 is, again, 14 oxygens. So we end up with an even number of oxygens here, meaning 14 divided by 2 is balancing coefficient of 7 here still works, and all we need to do is balance the number of carbon. We have 6 carbon in our reactants. 2 plus 3 plus 1 is 6. So we see, because we have multiple locations to balance carbon and oxygen, we can see that with incomplete combustions, it's actually easier to come up with a solution to the balancing because there's more than one way to balance every incomplete combustion reaction. Now that you've learned about all four of these strategies for balancing, see if you can apply your knowledge to successfully balance all of the chemical reactions below.